In this video, we want to investigate the continuity of a couple of functions. The first function we'll look at is the function f of x is equal to cosecant of x. We call cosecant is defined to be 1 over sine of x. And so looking at this, you should immediately start worrying. You can say, where are the bad things going to happen? Where might I have holes or jumps or vertical asymptotes? And because it's 1 over something, you know that bad behavior will happen where the bottom is equal to 0. So let's go back and try to recall sine. Sine on your unit circle is just the y coordinate. And that will be 0 at angle 0. And then again at angle pi. And then again at 2 pi, 3 pi, 4 pi, and so forth. And same with the negative direction. And so we know that sine of any multiple of pi will be equal to 0. So if you were to graph this cosecant function out, you would know that at every multiple of pi, so at pi, at 2 pi, at negative pi, at negative 2 pi, also at 0, you would have these vertical asymptotes that you have to worry about. Now, everywhere else, your function is simply going to be a nice continuous motion, right? Like if you think between 0 and pi. As you go from 0 to pi, your sine is going from 0 up to 1, down to 0. 1 divided by that is going to flip it to make it look something like this. You might remember this is what the graph of cosecant looks like. And over here it's similar. It's alternating up, down, positive, negative. So it's nice, continuous. There's no bad behavior except for at these multiples of pi. And so we'd say this graph is discontinuous. It's discontinuous at multiples of pi. At x is equal to any multiple of pi, where n is some integer multiple. Or if you want to say where this function is continuous, we'd say this function is continuous on, and we could use interval notation. Everywhere between 0 and pi, it's nice and continuous. Not at 0, not at pi. That's where I use parentheses to indicate not including 0, not including pi. But then also everything from pi to 2 pi is nice and continuous. And so forth in both directions, you know, from minus pi to 0, and so on and so on and so on. Okay, so hopefully that gives you some sense of the continuity of this graph. We've just identified the only places where it's not continuous are the multiples of pi. It's continuous everywhere in between those multiples. Now let's look at a rational function and see if we can do a similar analysis. Let's consider the function g of x is equal to x squared minus x minus 2 all over x squared plus x minus 6. And again, when you look at this, you know, okay, there's going to be some bad behavior when the bottom is equal to 0, so we should be on a lookout for that. But a good first move would be, let's try and factor this guy and see if we can get a better sense of what's going on in this fraction. So the top, you have a minus 2, so that would be a 2 and a 1. If you make it x minus 2 and x plus 1, that will factor it. Here I have a 6. Let's try 2 and 3. If I make that minus 2 and plus 3, that will factor it. And notice then you have two different pieces on bottom. One of the pieces, x plus 3, it does not cancel thing on top, whereas the other piece, x minus 2, does cancel with something on top. And you remember those two different pieces correspond to two different types of behavior. When there's canceling, that corresponds to a hole in the graph. Since the x minus 2 canceled, there's going to be a hole where x minus 2 is 0, that is where x is 2, you're going to have a hole. Since the x plus 3 did not cancel, you're going to have an asymptote, a vertical asymptote where your x plus 3 is 0. That is where x equals minus 3, you're going to have a vertical asymptote. And so if we were to sketch a little graph of what's going on here, not sure exactly what this graph looks like, what this graph looks exactly like. We do more analysis to get a better picture, but the essential information is here. At -3, 1, 2, 3. At -3, there's going to be some kind of vertical asymptote there. And at x equals 2, 1, 2, there's going to be some hole in the graph. And so I don't know exactly where that hole is. We could analyze it, but wherever it is, there's some hole. So your graph will look like however it looks, but there'll be a hole in it. So this graph has two places where it's discontinuous. This is discontinuous at x equals -3 and at x equals +2. At -3, this is a non-removable discontinuity. There's no way to get rid of it. But at 2, notice this is a removable discontinuity. If you were able to just plug in one point, you would be able to get rid of that discontinuity, so we call that a removable discontinuity. Instead of saying it's discontinuous at those points, we could instead describe where it's continuous. We could say it's discontinuous everywhere else. And so we would instead say it's continuous on the interval, everything up until -3. So from all the way in the negatives, -infinity to -3, not including -infinity because it's not a well-defined value, not including -3 because it's not defined there, union everything from -3 up until 2, not including the 2 because it's not defined there, and then everything from 2 off to +infinity, but not including +infinity. So I'm using my round bracket notation, my parentheses, to indicate not including those values.